Hey guys, welcome to our presentation on static electricity. In this deck, what we'll do is lay the foundations for all of our topic on electricity. So static electricity, where charges don't move, current electricity, where it does move, and so on. So what we're going to do is dive in with an important historical thing that's taught in grade schools. But what we want to do is add maybe significantly to what you know about it. This is the Benjamin Franklin experiment. So everybody started the story. You've got Benjamin Franklin, you've got a kite up here, we've got a nice silk wire that's going to travel down, and I don't know, there's a key somewhere in here where sparks can happen, and it was awesome. It was lightning, right? There's so much that's missing from that telling of the story. To begin with, the second scientist who tried to duplicate this experiment was a scientist in Russia who was electrocuted and died on the spot. Second of all, this is Benjamin Franklin and his son William. And apparently it's told in the story that William helped his dad with these experiments. Here's the story. What Franklin did was incredibly risky, but the science that he did was also groundbreaking. And the science that he did was so cool that it gave him the cachet. It gave him the international reputation to go and represent the United States to France and form relationships at a time when people in Europe probably could not have cared less about anything that was going on in this country. So to begin with, lightning, so thunderclouds, kite, silk thread that was wet, so it sort of conducted electricity. The key was really just there to show that he could draw sparks from the key, proving to everybody that he was drawing electricity down this little silk wire. But the key thing that nobody talks about in elementary school is down here at the bottom. So drew a little red circle around this thing called a Leyden jar. What you see in the right-hand image is a whole bank. Franklin invented the word battery, full of Leyden jars. And what Franklin did with this Leyden jar was he charged it up. And what he was doing back in the lab were experiments where he would rub tree sap that had hardened. It was called amber. He would rub glass on things like silk, rabbit fur, paper, and he drew static charges from these things. And he put those charges onto Leyden jars. And he did various experiments where he proved that opposite charges attract and like charges repel. But the fundamental thing that's really groundbreaking about the experiment is that Franklin proved that the lightning or the charge that he drew from the cloud was the same as the charges that he had been drawing off of rabbit's fur and silk and glass in his lab. So really enormously groundbreaking, and it sets the stage for the understanding that we have of matter today. And it was 1752. It was way ahead of its time, and it was really cool. Final thing, in class, ask me about the crazy stuff the Founding Fathers did with electrostatics. They were a bunch of goons. Okay, so moving on. The Coulomb experiment is one that we'll refer to quite a bit later. What we've done is we've just painted one of these little charges down here red. So we've got a little guy we're going to chart called Q1 in this experiment. And this little guy over here is Q2. Anyway, this is a thing called torsion balance. So very briefly, just a few decades after Franklin's experiment, Auguste Coulomb in France did the first quantitative experiments with static electricity. This thing called the torsional balance is so cool. What we have is this little dumbbell shape in the middle. And what we do is charge up Q1 and Q2 the same. And what happens is the little dumbbell twists. But because they knew the twisting force required to twist that fiber of silk, they were able to find out the very weak force that was going on depending on how far this thing had pushed. And based on that, Coulomb deduced that the exact formula that Isaac Newton used for gravity, the shape of that formula, worked perfectly. That Q1 is the amount of charge on the first object, Q2 is the amount of charge on the second, and R is the distance between Q1 and Q2. So plenty more on that later, but the torsion balance is an incredibly elegant experiment. I hope you noticed that what they did here was by hanging it the way they did, they enabled them to eliminate gravity as a force because of the symmetry of the thing. So super cool experiment. The next one is a lot more modern. So flip forward over 100 years, and we get a guy named J.J. Thomson. And what Thomson does is kind of Franklin-esque. What we've got is a thing called a cathode ray tube. So what we've done is we've got a battery. So there's a battery with a negative pole up here and a positive pole here. And this whole plate right here is going to become charged negative. This whole plate is going to become charged positive. What we do then is we heat up this metal plate and make it warm and make it in fact glowing hot. And what happens is, because of the presence of those two things, because this is hot and because we have a voltage here, we call them electrons now, but they were called cathode rays then. Rays zip off of this back plate and zing towards the front one. And if they're lucky, they get through this hole in the middle of the front plate. What Thomson does is to make the cathode and this front plate called the anode out of every metal he could get his hands on. And what he showed was that regardless of what the metals were, the rays that came out always behaved the same way. So that when he took a second battery and made a positive and negative plate, the charges always bent upwards towards the positive plate and always bent away from the negative plate, because electrons, we know, are negatively charged. So what it did was it demonstrated clearly that there's really a simple building block that's shared by all atoms. And we know it as the electron today, but it was a groundbreaking discovery, and it's relatively recent. So anyway, just a couple decades later, we really get what the value of that electron is. And the millikin oil drop experiment is very, very elegant also. Long story short, we spray tiny droplets of oil that are given a charge. And if you play games with plus and minus plates again, you can balance those charges and actually get them to hover. And so when you get them to hover or move up and down at steady speed, you're in a position to figure out the up force on them. So by knowing the droplet size and by knowing that they were oil, they could figure out the weight, the downward pull acting on the droplet. When they could figure out the upward pull, then they had some information about the strength of the charge force going on. And what it all came down to was that all of those oil droplets were carrying some multiple of that number right there. And so at the end of the deck, we'll get to that. We'll give you a couple of simple examples about how we use that in the early part of the chapter. To round it out, what we'll do is just leave you with a couple of factoids about the types of real-world materials we're going to deal with. In grade school, people learn about insulators and conductors. Conductors allow charges to pass through them. Insulators don't. In sophomore year, you may remember doing some work with S, P, D, and F orbitals. And we talked about alkali metals living here on the periodic table, right there. We talked about noble gases all the way down here at the end, but we talked about non-metals being kind of like this jaggy area in here. We had some metalloids, things that were sort of metallic right there, and we had all these guys right in here, which are the transition metals. These all are right down here, the actinide and lanthanide series, they're also metals. Anyway, most of the periodic table is metals, and what we're going to get is, at the end of this topic, we'll set the stage for a later discussion, which is where we really get to the real reasons why insulators and conductors behave the way they do. Just going to give you a hint right now before we get to our little sample example problem. So here's the idea, that when we make a wire out of gold, the behavior of the atoms inside the wire actually change because they're close to each other. So what's going to happen is, inside the metals and things that are good conductors, it's easy for an electron to pass from one atom to another atom to another atom to another atom, and so on. And what that has to do with is a thing called molecular band gaps. And the idea is that the band gaps inside of metals are small, which makes it easy for electrons to hop from one atom to another. Plenty more on that later, and we'll deal with it in a really a rigorous way. But I wanted you to hear the word early on. So finally, we're just going to go to a couple of math examples now. This is a pretty straightforward one where we've got a thundercloud that may carry 10 coulombs of charge. That turns out to be a hellacious amount of charge. By the way, if they had wanted us to know that it was a negative 10 coulomb thundercloud, they would have told us that. And so there's a little subtle thing that's built into this question. So what we're going to do is, first of all, just the math. So if we take 10 coulombs and use our Coulomb constant, or a charge on the electron, we know that every electron has a charge of 1.6 times 10 to the negative 19 of those coulombs. And what that tells us is that it's going to be, let's get our calculator, 6.25 times 10 to the 19 electrons required to make that 10 Coulomb charge possible. So finally, how did they move? Well, electrons are negative, protons and atom cores are positive. And so what has happened if this cloud became positive was it must have lost that number of electrons. So electrons were removed, which is how a thing becomes positive. Okay, so just a little review of electrostatic math there. All right. Second thing, also pretty straightforward, kind of same thing but opposite. If a woman walking across a rug collects 1.25 times 10 to the 14th, let's write that down, electrons, that's easy enough for us to go ahead and figure out, same idea, what happened. So one electron is going to have the same charge as it did before, so 1.6 times 10 to the negative 19 coulombs. And we go ahead and pull the trigger on this, and we get that's 0.00002 coulombs of charge, which is 2 times 10 to the minus 5 coulombs of charge. So that doesn't sound like a lot, but that's enough that a human being can give another person a spark, and they might go, wow, and they might jump. So again, a coulomb is a huge amount of charge in real life, even though it's only one of the thing. Part B of the thing, in reality, in physics, it's really going to be a thing that we stress all the time, that you need to be fluid with the metric system. So it's a thing that we work on throughout the year. It's always there. So if it's a thing you want to practice with me, let me know. So to convert this charge, 2 times 10 to the negative 5 coulombs into microcoulombs, all I'm going to do is just take coulombs, put them down here so that they cancel. We've got our good old factor label idea going on here. We've got microcoulombs here. One of the big ones equals a lot of the little ones, so 1 times 10 to the 6 microcoulombs. And what we're going to figure out is this woman's carrying 20 microcoulombs of charge on her person. Okay, so that's the intro, and we'll see you soon where we get deeper into the math and the concepts. So have a great day. Take care. Bye-bye.